Hi guys, welcome to Safi Mix back, and I want to continue from where I left in our last video. So I would need this one equation, equation 8 and equation 9 in the, I have made a mistake here. This is K1 and this is K1. And the wave function in this region, remember this would be like this at the boundary. So I first want to write the wave function psi 2x that we know from our previous video is equal to c times exponent minus k2 times x. That's the wave function. So I rub out all these things and want to rewrite the two equation 8 and equation 9 at these positions. So you know b equals k1 minus iota k2 divided by k1 plus iota k2 times a, and c equals 2 times k1 divided by k1 plus iota k2 times a. So this is equation a from our previous video, and this is equation 9. And now we want to use this equation to further understand, to get further insight into the problem. And there are three different quantities that we can use to analyze the problem. The first one I want to do is the probability flux current density. And the probability flux current density for a wave function is defined by iota h bar divided by 2m into psi of x derivative of psi of x with respect to position minus psi steric x into derivative of psi of x. This is psi steric divided by dx. So this is the definition of the probability flux current density. And now we want to find the probability flux current density for incident wave. So I will plug in this wave function into this equation, and I write J incident. I put I and C in the subscript to realize that we are dealing with the incident flux density, current density. Then I write iota h bar divided by 2m into a times exponent iota k1x for this, and the derivative of psi 1x is in fact equal to iota k1 times a exponent iota k1x, and then minus the steric of this O. This is the steric, so I would have a minus over here and a minus over here because you are taking the derivative of the complex conjugate of this wave function. So then the complex of this wave function is in fact a exponent, and here is steric. Here is also steric under probability amplitude minus iota k1x. And then the derivative of this wave function is in fact equal to iota k1 times a exponent iota k1 times x. And now a times a steric makes this a mod square. So I write this as iota h bar divided by 2m into, here is iota k1x, here is iota k1x. So I can take iota k1x common. Here is a times a mod, and here is a times a steric, and here is a steric times a. So I can take these terms constant. I can write iota k1, this, and then a mod squared. And then this exponent iota k1x multiplied with this exponent minus iota k1x gives me 1. And then minus 1 because there is a minus. And here I have minus, and this exponent minus iota k1x with this exponent minus iota k1x gives me 1. So I have minus 2 over here, and here is 2. I can cancel that with that. And this iota with this iota gives me minus. So that minus with this minus make it plus. And I am left with h bar k1 divided by m into a mod squared. and I give this equation 10. Now, instead of the incident wave, if I put the reflected wave into this one equation and carry this step like the one and this one, I get J reflected equals minus H bar K1 divided by M into B mod square. I call this equation 11. So we have the value for the current density of incident wave, the value for the current density of reflected wave, and if we look over here, the transmitted wave is real because K2 is a positive constant, X is positive, therefore this is a real wave function. And for real wave function, we know that the current density goes to 0. That's the property of current density. So I'm not making the calculation and I just use the property, but do put this wave function into this one equation and you will see that the transmitted current density goes to 0. So I just use the property and I write the transmitted current density equals 0. Now, let us the transmitted current density is 0. This in fact gives an insight that no particle has been transmitted into that region. But remember, that's not the final result. That's not the conclusion. We can make the conclusion from another quantifier. Now, from these current densities, I can define the reflection coefficient and the transmission coefficient. So I just want to write this equation here in this form. J incident is equal to H bar K1 divided by M mod A squared, and I call this equation 10, and this is equation 12. So I remove this and I remove this and I carry the calculations here. I think I should change the pin 2. So the reflection coefficient R is defined as the modulus, the ratio of the modulus of these two quantities, the incident and reflected. So I write this as J reflected divided by J incident mod gives the reflection coefficient. And if I put the values, I can write this as minus H bar K1 divided by M B mod squared divided by, and this will become mod because we have mod over here, and then H bar K1 divided by M mod into M mod squared. This cancels with this and we are left with B mod square divided by A mod square. And to further evaluate R, we need to find the B mod square, and that I can find from here. And we know that B mod square is in fact equal to B into B steric, and that would give me this term multiplied with its complex conjugate, this term multiplied with its complex conjugate, and this term multiplied with its complex conjugate. So using the properties of complex conjugate, the numerator I can directly write as K1 squared plus K2 squared, and then the denominator would become K1 squared plus K2 squared, and the modulus of S mod squared. This cancels with this, so B mod square is in fact equal to A mod squared. And if I put this value at this position, that gives me the reflection coefficient is 1. And similarly, if I find the transmission coefficient, the transmission coefficient by definition is given by the J transmission divided by J incident mod, and that's of course J transmission is 0, so the transmission coefficient is 0. Again, the transmission coefficient being 0 and the reflection coefficient being 1 tells us that no particle has been transmitted into the second area, into the region 2. But again, neither we can, but again we cannot conclude the result neither from this value or from this value, because there is another quantifier, the probability density of the wave function. And the probability density of the transmitted wave function is in fact equal to this thing. The probability of transmitted wave is in fact given by the psi 2 of x mod squared. And if I find, I remove these things, these things are not needed anymore. So I want to find this thing, and if I substitute that value and the value of C, I can write this as 2k1 divided by k1 plus iota k2 into 2k1 divided by k1 plus minus iota k2, and then multiplied with this twice, so I can write exponent minus k2x multiplied exponent minus k2x, because one for this is in fact equal to psi 2 of x into psi 2 of x static. So that's why I'm multiplying this and this. This is real, so the sign is not changing. And this gives me 4 k1 squared, and the mod of this gives me k1 squared plus k2 squared. And I miss one thing more, because this is A, so I have an A at this position and A steric at this position. That makes this thing equal mod A squared exponent minus 2 times k2x. This is the probability density of the particle in the second region. And if we look into this, all these terms, this multiplicator term is positive. So we have a positive constant multiplying with this exponential, and the argument of this exponential is also positive, because we know k2 is in fact directly proportional k2 is directly proportional to the difference V0 minus E, the incident energy. So that means larger this difference, larger the value of k, and larger the value of k, faster is the decay of this function with distance. Smaller this difference will make this decay slower. So, and for x equal to 1 over k2, the value of x which numerically becomes to the value of k2, we get exponent minus 2. And this is obviously negligibly small. So this equation tells us that the probability is non-zero but decaying very fast with the increasing value of x and the increasing difference between V0 and E. For fixed value of V0 minus E, this thing, the decay depends only on x. So what we have a wave function like this. And this becomes negligibly small for x equal to 1 over k2. Like we see over here, that becomes exponent minus 2. So this probability density tells us that we can find the transmission of the particle with this value. However, that decreases very gradually, and for x equal to 0, if I set x equal to 0, it is exactly equal to this thing. That is, closer to the boundary, we have a sufficient probability for finding the particle in the second region. So the particle transmit, and this is in contradiction to the classical version. This is peculiarly, this is typically quantum mechanical. So quantum mechanics say that closer to the boundary, there is a probability of finding particle in the classically forbidden region. Now, what is making this thing? If we look to this problem through uncertainty principle, and I'm writing a result here directly, it is straightforward to, one can prove that the uncertainty and position can be linked to the inverse of K2. And then the momentum uncertainty, the momentum position uncertainty principle gives us delta P equals approximately equal to h bar, allows us to write delta P is of the order of h bar over delta x, and placing that value will give me h bar divided by K2. And with this uncertainty in momentum, we can find the uncertainty in kinetic energy. The uncertainty in kinetic energy is then given by delta P squared divided by 2m, and that allows me to write delta P squared is equal to, this is the inverse of K, so this gives me K2, not divided by K2. And if I put this value, it gives me h bar squared K2 squared divided by 2m. And this must be equal to the difference V naught minus E. Or another word, I can write this as delta T plus E equals V naught. That is, the uncertainty in final energy is equal to V naught. Another word, the uncertainty principle washes the memory of the particle to let it decide whether my energy is lesser than V naught or equal to V naught. So it is this uncertainty in energy that gives the probability for the particle to move or enter into the classical forbidden region. In fact, the uncertainty principle explains that we can find with certain probability close to the boundary the particle in the second region. Okay, at the end, thanks for watching.